Okay, good morning, good afternoon, good evening. Welcome to the webinar. Today is our great pleasure to have Professor Paolo Sossi speaking with us from ETH. So Paolo started his higher education in Australia. First, his bachelor's at University of Adelaide, and then PhD at Australia National University. Then he moved to Institute of Geophysics in Paris for 4 years of postdoc, and then he moved to ETH first as a Swiss National Foundation postdoc fellow, and then assistant professor positions. His current position is. So Paolo has been serving as the counselor of European Geochemistry Association in 2024, and so that's the associate editor position for ICARIS. And Paolo's research is mainly focused on the formation of the terrestrial planets in our universe. So today he's going to present that part of his work is related to the moon. So with that, I will give the rest time for Paula. And this is a webinar that's relatively flexible in the format. So we normally we ask speakers for about 4 minutes, but feel free to speak shorter or slightly longer than that, and then we will leave some time for our discussion. And today's talk is recorded and will be posted on YouTube for Outreach for Science. So everyone who missed the talk could watch it online. Okay, with that, Paula, please.
Well, thank you so much for the generous introduction. It's a pleasure to be speaking with you today. And as mentioned, the topic is the composition, structure, and origin of the moon. And so just to calibrate where this is coming from, we were asked to write a treatise on geochemistry chapter a couple of years ago. And this is the result, combining geochemistry, planetary dynamics, and geophysics to get a hopefully better and more holistic understanding of the origin of Earth's nearest neighbor. So with that said, starting with a bit of context as to what was the common thinking throughout much of the late 20th century, this concept of a giant impact was recognized as a sort of natural progression of planet formation in general. And so there was this influential paper by Safronov in 1969 that described the nature of collisions that are driven by gravitational forces between smaller bodies known as planetesimals. And of course, as these planetesimals grow, they get larger, more massive, and these impacts therefore become more energetic. And it was thought that, particularly after the Apollo missions, you could have had some sort of Mars-sized impactor that collided with the proto-Earth, and that collision would have been sufficient to explain the present-day angular momentum of the Earth-Moon system. And this is why, because of these physical benefits of such a process, why this theory became such a widely held notion in the community. Now, one of the major predictions of this model is that most of the material comes from the impactor. And so you can see in this simulation animation from Robin Canup that, of course, none of these simulations actually end up forming a moon, but on the basis of the material that is flung out into orbit, you can see that it's mostly this yellow matter. That material would have come from the impactor and eventually gone on to form the moon. So this maybe seemed to be satisfactory for all current observations for all intents and purposes. So we think, okay, perhaps the problem is solved. We don't have to work anymore on the issue. The problem started to arise in about 2001, where it was recognized that the moon, shown in these white circles here, in terms of its oxygen isotope composition. Now, when I speak about oxygen isotopes, we have both delta 18 oxygen and delta 17 oxygen. And if you look at the deviation from this terrestrial fractionation line, you can see that these deviations correspond to rocks that come from different celestial bodies. And so they're used to then fingerprint where material comes from in the solar system. And for the moon, as you can see here, it lies squarely on the line that is defined by rocks from the Earth. And so this is quantified in terms of its cap delta 17 oxygen, and what this means is that, okay, perhaps we have either the moon and the Earth coming from the same material, Or, of course, because we're only looking at this one particular isotopic system, that it could simply be a coincidence and they come from very, very close spatial regions in the solar system. Now, this left some interpretation, of course, but since then, as you likely know, there have been a number of different isotopic systems that have been measured in both the Earth and the Moon, and of course in other um, sort of meteorites and other samples that have gone on to attest that the Earth and Moon are not only identical in cap delta 17 oxygen, which I just showed you, but also in the isotopic composition of chromium and of titanium. Now, these isotope ratios are not able to be changed by internal differentiation processes, such that if you start to fractionate mass dependently these elements or these isotopes, then this epsilon notation will remain unchanged because you normalize two different isotopic ratios within that sample. And so these are insensitive to other evaporation, core formation, and so forth. And so what this implies is that in addition to now many more systems, that the Moon and Earth were indeed formed from the very same material. So this is now, of course, a problem for this traditional theory that you have most of the material coming from the impactor. So what could explain this immense similarity between these two bodies? So the first is, of course, you can appeal to happenstance and say that actually, okay, there were two bodies in the inner solar system that both had some very similar isotopic compositions, and you had some, therefore, moon or Earth-like moon-forming impactor. And so what this would predict, of course, is that you do have, it satisfies this condition that the isotopic compositions are the same, but it doesn't necessarily mean that the chemistry of the moon is identical to that what you would expect had you inherited the moon from the Earth directly. And so there's a testable hypothesis there. The isotopes would be the same, but the chemistry could be different. And in this case, you would be able to invoke this more canonical model with a Mars-sized impactor. The other possibility is that indeed the moon formed from material that had initially already accreted to the proto-Earth. And in this case, you would perhaps fling material out from a proto-Earth mantle after differentiation of the core. And the reason why the core already has to have formed will become clear as the presentation progresses. And so in this case, there's a slight difference because you do have the same isotopes again, it comes from the same material, but now also you have some sort of inheritance of the chemistry as well that was imprinted upon the Earth's mantle due to core formation. And so in that case, the canonical model would not be satisfied. And so we would have to think of different dynamical scenarios that would cause this moon formation process. Okay, so clearly we have two models, one in which the chemistry is different, the other in which the chemistry is the same. And so if we can determine what the composition of the moon is, we can go some ways towards testing these two ideas. Okay, so the sort of consequence that these impacts and collisions were taking place during the early stages of Earth's formation implies that the energies that were delivered were sufficient to entail or to cause entire wholesale melting of the moon. And so there are a number of lines of evidence that we have to support this hypothesis. And these are in the form of the rocks that we can actually measure and sample from the moon, the fans, Faroan anorthosites, and the Mare basalts. And so these sort of two major lithologies that we find on the moon are thought to have been complementary and created by the crystallization of the magma ocean itself, as you can see here. So the evidence, I won't go into all the details, but we have sort of complementary anomalies in elements like europium that are enriched in the fans and depleted in the Mare basalts. But also we have these two types of mare basalt, so low titanium and high titanium, which implies that their sources in the lunar mantle were poorly mixed. That is, you could preserve mineralogical heterogeneities that are thought to be vestiges of this crystallization process. So as a result of that heterogeneity, it is then very difficult to go out, as we do for the Earth, and find a rock or a series of rocks that are representative of the composition of the lunar mantle. We don't necessarily have any representative whole rocks, although I know that the Changi 6 missions are now finding particular grains of olivine and orthopyroxene that have very high Mg numbers and that have been interpreted to be from the lunar mantle. So I'm waiting to see where this story ends. But in absence of that, we have to find more creative techniques to determine the composition of the lunar mantle. And so I guess one of the enduring methods for doing so was to look at the range of compositions in highland rocks, as Ted Ringwood did in the 1980s. And so here what you have are, in these vertical lines, different whole rock compositions from the Faroan anorthosites. And you can see that there's some sort of linear correlation when you plot these compositions as a function of some sort of inferred primitive component. Now, that primitive component is defined by a chondritic calcium to aluminium ratio. These two elements are special because they are refractory lithophile elements, and so they're not fractionated neither by pore formation nor by volatility. And so the idea is that this ratio should be chondritic also in the moon. And so if you extrapolate these trends to a chondritic calcium aluminium ratio, what you find is that unfortunately the magnesium to silicon ratio is 0.77, which is too low to either reach a chondritic ratio or even that found in Earth's mantle. And so what Ted Ringwood did was to simply add olivine back with a very high magnesium to silicon ratio to satisfy one or either of these reservoirs and therefore compute the composition of the bulk moon. And of course, you can appreciate that that's a very non-unique way to determine the composition of the moon. And so I think we need better and independent constraints as to what the composition of the moon is. And so we have to turn to our friends in geophysics to do that. As you know, there were seismic stations, or there are still seismic stations on the moon, although they've now been shut down, unfortunately, in the infinite wisdom at the time to say, okay, let's save some money here and turn off the seismometers back in 1977. Nevertheless, we have 4 stations that were collecting simultaneously between about 1972 and 1977, and they recorded some 12,000 moonquakes in that time. Of course, not all of these moonquakes were sufficiently intense to be able to actually derive any kind of quantitative properties of the lunar interior, but nevertheless, it provided us with a very extensive database from which to start to map out the interior structure of the moon. This led, of course, to the Apollo-era seismic model, which was done by Nakamura in 1983, and you can see a sort of a schematic from that paper here. What you'll also notice, and what you also know, is that these Apollo missions landed all on the near side of the moon. And so we have a limited azimuthal coverage of the lunar interior. You can see the locations of deep moonquakes here. That means the far side is essentially unconstrained by geophysics. Nevertheless, this is a very good start for us and something that we can work with. The other problem is that these lunar seismograms are long duration and rather unstable because of the uncompacted nature of the lunar regolith. And so this means that although you can pick the arrival times of the P and S waves relatively well, any kind of subsequent arrivals or reflections are not well determined in these seismograms because of these very long and noisy coda that you see, and it's typical of a lunar. I think a geophysicist, anything worth their salt, will be able to see a seismogram from the moon and say that's immediately that's from the moon. So it's very particular in terms of its signal, and that means that we're limited for us in terms of the depth at which we can actually resolve any structure. So you can see here, this is the seismic profile that was determined by Nakamura in 1983. And if you know the radius of the moon is 1,737 kilometers, so we're only getting to about 2/3 of that here, about 1,000 kilometers depth. That's as far down as we can see from seismology in the moon. And so I guess the main feature of these seismograms that were taken by Nakamura were that you have this large discontinuity in the mid-mantle of the moon here, around 500 kilometers, both in VS and VP. Now, subsequent models have shown that actually this continuity is not necessarily required. So subsequent treatment of the lunar seismic data was done in the early 2000s. Amir Khan, co-author on this work, refined this in 2002, showing that there's not such a strong discontinuity. And indeed, the most recent inversions show that this is not really a robust feature of the lunar interior. Another point to note that is not immediately evident here is actually that these seismic velocities tend to actually slightly decrease as you go down in depth in the moon. And so this is probably due to an influence of temperature winning out over compression, because these are sort of two competing effects in determining VP and VS. And so that's another interesting feature which has not yet been really fleshed out. So we also have other data that we can use to constrain the lunar composition. This comes in the form of lunar laser ranging, and that enables us to look at the physical librations of the moon that are influenced by tidal interactions with the Earth. And if you combine these data with gravity data, you can obtain the mean moment of inertia for the moon. And that value is around 0.393112, so very precisely known. And maybe this number by itself doesn't mean much to you, but if you compare that number with that of a homogeneous sphere, which is 0.4, what this indicates is that the distribution of mass within the moon is very homogeneous. That is, unlike the Earth, which has a mean moment of inertia of 0.337, the moon essentially has the same distribution of mass throughout its depth. Of course, for the Earth, we know this is not the case because of the formation of the Earth's core. And that implies then that the lunar core must be very small. And so this already gives us some indications from which to start interpreting or building our combined geophysical and geochemical model. So we're not the first people to do this. And I show you an example here from Amir again in 2006. Where they tried to have this approach in which they incorporate these disparate pieces of evidence to build a compositional model for the moon. And what you can see here is a probability distribution function for each of the major oxides, the 5 major oxides that they considered in this study in the moon. Of course, this picture of the Earth here nicely illustrates what the Earth's mantle composition is. And you can see that, okay, if maybe for silicon and aluminium and calcium, there are some similarities, although I should mention for context, there was a bit of a debate about whether the moon was enriched in calcium and aluminium because of the thick plagioclase crust that was resolved because of the porosity that was actually not considered in these earlier models, but I'll leave that for another day. And so while these 3 oxides might be quite similar, the iron-magnesium ratio looks to be rather different between the Earth and the moon. So although it could be rather Earth-like, these particular elements maybe not. And if you look at the numbers here, the magnesium number, so the ratio of magnesium to iron plus magnesium is substantially lower in the moon than it is in the Earth. There are, of course, some limitations to this. So in many cases, minor elements are not included, although this is probably not a huge effect. And the main uncertainty, as I just mentioned, is that the core is poorly constrained because we only have seismic data down to about 1,000 kilometers. So what we wanted to do is to have a bit more of a systematic look at the effect of the composition of the moon on its geophysical properties. So the model that I just showed is a sort of an inverse model where you take a bunch of geophysical parameters and then you invert them to determine the composition. And here we want to rather impose a composition and say, okay, what would the geophysical implications of that composition be? And so to do that, we had to we took a bunch of proposed models for the composition of the moon, and we had to assume a homogeneous mantle. So this assumption, as you recall, is coming from this notion that actually there are no seismic discontinuities in the lunar interior. And so we think to first order, assuming a homogeneous mantle would be okay. Then we choose a relatively simple system. So we include titanium, but the other oxides are the same. We assume Earth-like and therefore essentially chondritic ratios of the refractory elements. And we model the core as a homogeneous sphere of constant density. So these are the different models that we looked at. And so these have been published in somewhat recent times. And we also had sort of a variable composition model. So this is something that the model or the sort of the calculation tells us should be characteristic of the moon. And these are the geophysical parameters that we use to constrain the models. So just to outline briefly the approach, we have these geophysical parameters, so density, mass, moment of inertia, as well as the K2 love number. And we feed all of these geophysical parameters in to a model in which we use these compositional values to determine the stable mineralogy at every given PT interval in the lunar interior. And so, of course, as the composition changes, the mineral stability also changes via Gibbs free energy minimization. And so because this code, Purple X, which is written by Jamie Connolly, enables us to tabulate these geophysical properties such as density and wave velocity, then we can use the properties that emerge from our model to then go and back calculate and see whether they are consistent with the known parameters and known values. And so that's kind of the output, and we can go ahead and then build models that are based on these calculations. And so that's what we've done here. So the different model compositions that I've just mentioned in the earlier slide are now represented here in different colors as a function of depth. We show the VP and the VS. And the target values are these sort of yellow train tracks here. So if the model is doing a good job, it should fall somewhere within these this yellow field. So there's a few things to highlight. That the first is, of course, that I should mention that the total amount of iron in the moon, it's in the bulk moon, including the core, including the mantle, is much, much lower, about a third to three-quarters the value of the bulk Earth. So we can't think of the moon as a sort of a typical planetary body because it's really super depleted in iron, in metallic iron in particular. And you'll see that these seismic models match relatively well in the lower part of the lunar mantle. So there's not much of a distinction between them. Perhaps the iron-rich model of Taylor is a little bit out, but the others are more or less okay within the uncertainties. We have a core radius, that is around 300 plus or minus 20 kilometers in diameter, in radius, And so this, because the radius is relatively constant and the density changes, that means it represents different proportions of the lunar mass. So the higher density core would represent around 1.5% of the mass of the moon, and the lower density core would represent around 0.8% of the mass of the moon. So the other feature that you might notice is that these blue models, which are the higher magnesium number models, tend to provide a poor fit for the seismic data in the uppermost lunar mantle. And so these are slightly faster than what we would expect and also have sort of different densities, perhaps. And so what we can glean from this is that if these high magnesium number models are correct, then the moon cannot be homogeneous, because that was our initial assumption, to say, okay, well, these are all homogeneous in composition. But you can see here that the upper part of the lunar mantle is more consistent with an iron-rich or somewhat more iron-rich bulk compositional model, such as that of Hugh O'Neill or Amir in 2006, or Nicolas Dauphas. And then in the deeper part of the moon, then all of these models are consistent. So we need this idea that there's a high magnesium number lunar mantle at the top of the lunar mantle doesn't seem to be consistent with seismic data. So the interesting thing is that you can now sort of plot our assumed lunar bulk composition against the core density. As I mentioned, the core density has a large range, and that range correlates with the magnesium number of the lunar mantle. And so this is clear when you start to think about it, because if you consider that the mass of the moon has to be conserved, if you put more mass into the mantle, that is by having an iron-rich mantle composition, then you have to subtract some mass from the core, right? And so this means that you have a difference in the core density as a result of a difference in the mantle magnesium number. So it's a zero-sum problem. And so these differences in composition, if we think that the core is largely iron-nickel rich, must come from a different complement of light elements. The problem is, of course, that the moon is thought to be nominally dry, so we don't think we have much carbon or hydrogen available in the moon to actually go into the core to lower its density. So we have to think about ways this could happen, and probably the most likely candidate, as you can see with this dashed yellow line here, is sulfur. So let's go ahead and sort of assess that possibility a little bit more closely. So here, what I show is the density of the FeS eutectic or sulfur-bearing iron metal composition in black, and in red you see the sulfur content in the core that is required to calculate that density, or to achieve that density. So if you assume that there's no sulfur in the lunar mantle, in order to achieve this value of about 5,000 kilograms per meter cubed, you need 25 weight% sulfur in the core. Is that a reasonable number? Let's assess this logically. So if the moon has lost around 3/4 of its iron content relative to the Earth, as I mentioned in the previous slide, then the maximum amount of sulfur would be around 2,500 ppm. But if you look at the lunar mare basalts, they are already depleted in addition by a factor of about 4 compared to the terrestrial basalts. And so what this means is that there's probably less than about 250 ppm sulfur in the moon total, which gives us an upper limit of about 2% sulfur in the lunar core. Sorry, around here, this gray bar. And so this doesn't bode well either as for sulfur as a means of lowering the density of the lunar core. So that means we're a bit stuck. I didn't profess to have all the answers. That's why we're still working on it and thinking about the moon, which is great. So you may be familiar with these models, the Rene Weber in 2011 about a sort of a multi-layer lunar core. But as I mentioned earlier, we don't really have any seismic data for these depths. And so really picking out any particular layers or inferring compositions from this is difficult and ambiguous. So I wouldn't take this necessarily as Bible. There is some evidence that there's probably a partially molten layer somewhere, because that's required to match the K2 love number constraints, which I didn't mention in detail. And the iron nickel rich composition, which would be consistent perhaps and is easier to explain in terms of a volatile budget, would be more difficult than to explain the higher to explain the K2 love number. And so there are pros and cons with each either volatile core or volatile rich lunar core model. So maybe if I have still a bit of time, I can just delve into the geochemistry a slight bit. I might skip a couple of slides, but essentially we can now use geochemistry to sort of gain better constraints as to what the composition of the lunar core is, and indeed the lunar mantle. So again, the observation that the tungsten to uranium ratio in the Earth and the Moon, so terrestrial basalts and lunar basalts, is very similar, again leads to this notion that perhaps we had some connection between the Earth and the Moon. So that connection not only extends to tungsten and uranium, but also these mildly siderophile elements, magnesium, chromium, and vanadium. So if you compare the Earth and Moon abundances of these three elements, you can see that they are different to other planetary bodies. So this is a very old plot. So this is SPB, is the Shergottite parent body, so which we now know is Mars, and the Eucrite parent body, which we think is Vesta. And so compared to Mars and Vesta, the Earth and Moon are very unique and again, very similar to one another. So because these are weakly siderophile elements, as I mentioned, there's very little ways in which you can fractionate them easily on these bodies. And as you can see for the Eucrite parent body, actually they're not fractionated. And for Mars, it's a bit less clear. So probably not by volatility, and certainly not by core formation for vanadium. And so there's again two options. One is that you can form or you can deplete these elements by core formation on the Moon, or they were inherited directly from the Earth's mantle. So again, going back to our two initial hypotheses that I set out at the start. I'll probably skip this just to say that we can use the abundances of iron, nickel, and chromium to determine what the composition of the lunar core is. And just going through the basic exercise, we want to make a mass balance calculation and mass action calculation so we can conserve mass, but also are satisfying the thermodynamics of element partitioning between core and mantle. We can determine a relatively good estimate for the lunar core. So I'll just go here and show you that it looks like the lunar core formed at around 5 GPa and maybe close to 2000 Kelvin. So this gives us some pressure temperature constraints from which to model how siderophile manganese, chromium, and vanadium should be during core formation on the Moon. And the partitioning also tells us that it probably occurred at relatively oxidizing conditions. So if the Earth is at delta iron wustite minus 2.2, the Moon is about 1 log unit more oxidized than that. And that's the reason why you get relatively high nickel contents in the lunar core, and that's needed to fit the nickel-cobalt ratio that you measure in particularly the lunar pyroclastic glasses. And so that's where these sort of constraints tie in with one another. Okay, so we have some information now about the conditions under which the lunar core formed. If we now compare that to the siderophility, so that the likelihood that manganese partitions into metal under these conditions, you can see that manganese, so this plot here shows the log KD, so that's the partition coefficient of manganese between metal and silicate divided by the partition coefficient of iron between metal and silicate. And that value is relatively low, so it's less siderophile than iron is, so it's below 0. And indeed, it's only only gets to relatively high values, even -1, by 20, 30, perhaps GPa, and very high temperatures, which I've just said, of course, did not seem to characterize core formation on the Moon. So if we think that, then if we want to appeal to core formation on the Moon to explain these depletions in manganese, chromium, and vanadium, then the core of the Moon is simply too small and formed at too low pressure and temperature to be able to actually partition sufficient amounts of manganese into the lunar core. So my interpretation, and I think this is sort of, I can't really take credit for this, but Ted Ringwood said this in the 1970s. But it seems to me that the best explanation is that the moon had to have formed from the Earth's mantle after Earth's core formed, because the core formation on the Earth is the only process that we seem to have that reached these kind of extreme temperatures and pressures that were able to remove enough manganese from the Earth's mantle and therefore from the moon. So that's my current thinking, but happy to hear other ideas. So tungsten. So this is another important constraint because again, hafnium is a lithophile element and tungsten is a siderophile element. So by looking at the hafnium-tungsten ratio, we can try and use that to constrain the timing and nature of core formation on the moon. And it's got a very short half-life, so it's just about adapted to look at this problem. So the interesting thing was that the moon has a small excess in tungsten relative to the Earth's mantle. And this excess could either be due to accretion of a late veneer or differential accretion of a late veneer on the Earth and Moon, where the Earth received a bit more, or that it could reflect residual core formation that occurred on the Moon that removed a bit of the tungsten relative to what's seen in the Earth. Either way, it looks as though that process started from an Earth-like tungsten isotope composition of the moon. So then Krauer and Kleiner performed a model in which they determined how likely it is that the Earth's mantle and the moon have the same tungsten isotope composition, obviously post this correction that I've described. And so what they've done is to say, let's calculate the possible range of 182 tungsten isotope composition of the pre-late veneer moon, assuming different impactor sizes, core formation ages, etc. And they get, therefore, a distribution of tungsten isotope compositions that could arise from this sort of more stochastic random process. And so then they highlight that if you assume that 80% of the moon is made from an impactor, so this is more a canonical scenario, then you reach the observed composition only in 1% of all the cases that they studied. And so this, again, indicates that even if you have an Earth-like impactor for the nucleosynthetic isotope compositions, it's again very unlikely that you would have exactly the same tungsten isotope composition, because that not only depends on the origin of the material, but also when the Earth's or the Earth and Moon's cores formed. And so as a result of that, again, the likelihood of that happening is just very low. And so if you then, of course, think about probabilities, they're multiplicative. And so you multiply all these very low probabilities and you get a very, very, very low number that this is actually true. So what does that mean? What mechanisms could have formed the moon? So again, there's a couple of ideas that have led to this stage. And so people have been getting creative as to different scenarios. And here is just a sort of a relatively compact summary of ideas that have been thrown out in the literature rather recently. So you have, again, the canonical model shown at the top of the slide. You have a multiple impact model where you have several impacts that it could eventually lead to the moon. This, to me, sounds to be unnecessarily complicated, given the similarity in the isotopes and the chemistry. You have this half-Earth model, which was proposed by Robin Caniff in 2012, and it was recognized in 2018 by Simon Locke and Sarah Stewart, that this sort of energetic impact would actually lead to a new kind of structure. So it's not a sort of a disk or a debris disk that might form after your typical canonical impact, but rather this sort of supercritical, at least initially, phase that therefore promotes mixing between these two bodies. And this is known as a synestia. And so all of these models have different implications. And what we wanted to do in the chapter was to see, okay, based on the orbital parameters that are required to generate these different sort of impacts, again, how likely are these dynamical situations to arise in an Earth accretion scenario? And so the first thing we did was to look at this was done by Miki Nakajima, to look at the statistics of impacts occurring in the Grand TAC model. And so we looked at N-body simulations for planet formation from Dave Ruby. These canonical impacts, as you can see here, would require an angle around 45 degrees and a impactor velocity to the escape velocity around 1. Again, the impactor to total mass ratio is, again, close to Mars-sized. And what you see is that these are relatively common impact types in the Grand TAC model for planet formation. And so we think then if you compare that to synestia-forming impacts, there's essentially no half-Earth impact. So this gamma factor, if this were around 0.5, then you would get a sort of half-Earth-like scenario and therefore potentially synestia, but these essentially never occur in the Grand TAC model. So if you were to believe this model, then you would naively think that, okay, this synestia thing is just not possible. But of course, recently there's been this push to look at other ways of forming planets, again, sort of motivated by observations of protoplanetary disks, notably HL Tau and others, that show these sort of ring structures in protoplanetary disks. And this has led to the development of a ring model. So Alessandro Morbidelli has been looking at this in some detail. And if you take that as an initial condition, then you see that the dynamics of these impacts are quite different. So again, the canonical conditions are fulfilled. So you have these 45-degree impacts, relatively similar escape to impact velocity ratio and impact to total mass ratio. But also you can see here that the impact to total mass ratio is now rather sort of a uniform distribution up to very high values. And so here it seems as though synestia forming impacts could actually be quite common. And so we can't really use dynamics at this stage to sort of discriminate between the likelihood of these two possibilities. So to finally finish up, this was an influential paper in 1986 at the Kona conference in Hawaii. And at the time, there were various models for moon formation, and they all had, again, sort of pluses and minuses. And so I think the author, I think it's John Wood, had the idea to sort of grade them as if they were an American school student. And these are the grades that were given. So these are the different theories here listed in the different columns, and the rows list the observations or the constraints that they had at the time. And you can see that there was no sort of consensus as to what the favored model was. But I thought we would sort of reproduce this with the present day information that we have. And again, it's similarly equivocal in the sense that we, again, don't really have a really favored model that explains absolutely everything. And of course, if we did, that would be very boring because then we can go home. But so here are a few things that these models explain better or worse. So the synestia model, as I mentioned, because it's equilibrating everything, it does a very good job in terms of making similarities within isotopes, but also potentially chemistry. It seems to do a poorer job for the angular momentum. Of course, that's the initial idea for the canonical model, that the angular momentum constraint is very well satisfied. There are ways perhaps to loosen that constraint, but I won't go into that here. The dynamical likelihood of canonical impact remains very high. Synestia is also potentially quite common. And so the lunar mass is also relatively well explained by canonical impacts. It remains really to be seen for a synestia. This could change in the future. So I want to finish by saying that all these impact models have problems, as I mentioned, and also maybe this is you'd come to this conclusion already, but if you just look at the chemistry, it's all inherited from the Earth. So there's no geochemical item that you can really point to say, this is a signature of the impactor. So I think giving an impactor a name is a bit silly if we don't have any actual evidence that there was any chemical trace of this impactor, probably because of homogenization, but who knows? So let's keep an open mind. And I'll finish here just to have a few final conclusions. So the bulk composition of the moon is similar to that of the Earth's mantle. We can hope to refine this with better geophysical data and geochemical data. The main uncertainty is for the FeO content. If the FeO content of the lunar mantle is similar to the Earth's mantle, the lunar core is relatively just binary iron nickel alloy. If the FeO content of the moon's mantle is higher than in the Earth's mantle, then the lunar core requires sulfur or some other light component, could be ilmenite as well. This has been another idea. The lunar core seems to have to be partially liquid and around 300 kilometers in radius, but these other properties in detail are not very well known. Again, just to reiterate, the isotopic evidence and the siderophile elements show that the moon really in all likelihood must have come from the Earth's mantle and not simply formed from Earth-like material. And there is no single model that explains all of the properties of the moon. So with that, thank you for your attention and happy to take some questions.
Okay, thank you very much, Paolo. Now it's time for questions from our participants. So feel free to open your mic to ask a question, or alternatively, you could leave their question in the chat, and I can ask a question on your behalf. So any questions? Okay, okay. Any questions?
Uh, yes.
Yeah, yeah,
Can you
yeah,
hear me?
yeah, yeah, yeah. Junjie, go ahead. Mhm.
Oh, hi, Paolo. Thanks for the
Hey,
presentation. So could you go back to the seismic profile with the petrologic model?
yep. This one here?
Oh, yeah,
Or,
this one. Yeah, I'm very
yep.
curious. I think it's very good work, and I'm curious about the temperature profile you have chosen
Uh-huh.
because so which temperature you have used for the whole mantle?
So the temperature is also refined in the calculation. So it's varied according to try and get sort of a best fit. So
Mm-hmm,
it tends to be a little bit higher for the Earth-like cases. So I think it's close to 1,000 Kelvin potential temperature. And the iron-rich cases tend to be a little bit colder from memory. So
Oh, okay. So actually,
around
it's
800.
so it's a little bit similar to the solidus of the pathological model.
It's maybe not the Solidus because a Kelvin, the Solidus is probably, yeah, maybe let's say 1100 Celsius. So we're probably at least a couple of hundred Kelvin below that. Yeah, but we don't explicitly have melting, for example, in the model. So this is not something we checked for. Yeah,
Okay, thanks. Mhm.
no problem.
The next question, please. Oh, okay, let me ask a question. Actually, uh, most of the lunar geologists in China, actually, they are at the University of Hong Kong now because they are going to have a two-day seminar this weekend on new
Okay.
progress on Chang'e 6 samples that have not been published. I'm not there. So actually, your talk is a
Okay.
very good pre-conference talk. I don't know whether they're going to see it or not, but we're going to post online, so it's pretty good.
Ah,
So
okay.
that's a question. Yeah, that's a question relative to Channel 6 that as well Channel 5 that those young magmatic rocks that people have been seeing. So where does heat source coming from?
That's
So
a very
so
good question.
yeah, yeah. So from your perspective, that how could they be generated at the middle age of the moon?
Yeah,
Well, not in
I,
the
I
time.
I'm not sure. I'm not sure if these basalts, do they have any creep sort of signature or not? I'm not sure. Do you know?
I don't know
No.
neither. I don't know
Yeah,
whether
so
there are other people in
maybe,
the room now. I don't know.
yeah, so maybe, I mean, the presence of creep could be one way of getting these radiogenic heat producing elements concentrated in particular zones
Mhm.
in the mantle. So I can think of, if you crystallize the lunar magma ocean right to the end, you think you get close to a creep-like component, and so if that is then sort of sits around in various pockets, let's say, in the lunar interior, maybe that's a way of locally generating a little bit of heat. And so you get small amounts of melting in discrete areas if that's because again, also the lunar mantle is very heterogeneous. So if you have sort of highly fusible material, so fertile material that can melt quite easily, and you put that in contact with the creep-like sort of component for a while, maybe that's a way of generating melting even today.
Unfortunately, as far as my recollection, the literature that I've seen is just opposite to that. That people,
It's
I
opposite.
mean, people, yeah, the absence of creep. I think that was the title of
Mhm.
one of the publications. So it's very odd
Aha.
to me.
That's strange. Yeah. I don't have a good explanation for that, I'm afraid then.
That's okay. We're going to see more from them very soon because I think people are busy publishing them nowadays.
Hmm.
Okay, next question, please.
Okay, yeah, may I ask another question?
Yeah, sure. Go ahead.
Yeah. So yeah, yeah. So in talk, there is also mentioned that actually the two sides of the not two sides, the whole moon is a little bit relatively homogeneous. I mean, the composition of the two sides should be similar because of the so many parameters shows. So but there is also some model, simulation models produced by the Macau group and also Peking group. They think there's a giant impact, is another giant impact which produced the SPA and also migrate some IBC or creep things from the far side to the near side. So actually, it would cause a very big difference between in ion contents between the two sides. Do you have any opinion about this kind of story, or you think it can? Yeah. So because it's a relatively homogeneous, so actually it cannot be one side is iron poor and one side is iron rich.
Hmm. Yeah, no, I think the problem is that this seismic data is just all from the near side. So if we had to use this data to constrain what's going on the far side, it's a little bit difficult, other than to say that, okay, is the is the composition that we pick for the seismic data consistent with the bulk properties of the moon, so mean moment of inertia, mass, and so forth. And so I think we don't yet have the resolution to be able to discriminate between, um, a magnesium-rich far side and an iron-rich near side. I think at the moment the uncertainties are too large to be able to say definitively, but I think it's something that we should explore because it means that we have an extra degree of freedom to play with. We could think about making the same model and saying, okay, well, what happens if you split the moon in two and
Mm.
say, okay, this is iron rich and this is magnesium rich. I'm not sure if anyone's done this, so that would be a fun exercise to carry out and see what the implications are for that. So yeah, and I agree that the South Pole Aitken Basin, a giant impact or some sort of large impact would be a reasonable explanation for that. And I think you're seeing these sort of high magnesium lithologies also excavated from there. So um, it seems reasonable at this stage.
Hmm. Yeah, perhaps we should wait for the future China project with a seismic meter on the near
Mhm.
side.
Mhm.
Exactly. Exactly.
Yeah, yeah, to me, if we are going to gamble now, I would probably gamble yes. There is a might be a difference from for example, you look at Mars, this is also possible. And this is a
Yeah.
biohemisphere signature. So that's the Earth in terms of the large low shear velocity provinces. That see that we might have this a degree two like compositional differences within a terrestrial planet mantle. So if I'm going to gamble, I'm going to gamble
Yeah.
both for that.
Yeah, I agree. I mean, I think also with Mars, they've got a bit. In some ways, it's less good because they have only one seismometer, and so they're
Mhm.
restricted in terms of triangulation and
Mhm.
sort of
Mhm.
locating these Mars quakes. But they also have impacts, and they cross correlate. Okay, where did this impact occur relative to the images that they have of the Martian surface? And so there are some waves that traverse relatively large swathes of the Martian interior. And so
Mhm.
I don't think there's also not a consensus as to, okay, there's a crustal dichotomy, that's clear, but is that also reflected in the mantle of Mars? That's not yet resolved either. So
Mhm.
yeah, it could turn out that these planetary bodies are much more complex than we think.
And depending on how much data we have.
Exactly. We need more seismometers.
Mhm.
Yeah.
Mm. Okay, more
Um,
questions. Okay, I think let's wrap it now. It's about 1 hour. It's perfect. Thank you very much, Paolo. And thanks everyone for your participation. I think the Chang'e 6 mission symposium occurring at the University of Hong Kong, they are going to pose more questions rather than answering
yeah.
all the mysteries we have been discussed so far.
Happy to hear about it. Yeah,
Yeah,
exactly. Well, thank you very much for the invitation and everything.
yeah.
Yeah.
Okay, see you in future conferences. Have a good day. Bye bye.
Thank you. Bye bye. See you, everyone.